We're going to look at next non-conservative forces. So conservation of mechanical energy, the fact that kinetic energy turns into potential energy, either gravitational or spring, and then back to kinetic energy, and you can go back and forth, again, like moving money from one bank account to another, assumes that all of the forces are conservative and that you can recover the energy you put in fairly. So you put $500 into one account, you can get that $500 back without penalty. There are some forces in nature that are non-conservative. For example, friction and drag forces are non-conservative forces. So you can break up the work done, right? Work is done by forces applying a force through some distance. You can break up the net work done on a system into two classes. You have the conservative work done by conservative forces, and the work done by non-conservative forces. And a force can't be both, right? It has to be one or the other. Well, we know from the work kinetic energy theorem that the total net work on an object is equal to that object's change in kinetic energy. So I just make a simple substitution. Instead of the net work, now we have the work done by conservative forces. The work done by non-conservative forces is equal to the kinetic energy change of a system. We also know previously, when talking about gravity, conservative forces are equal to the change in gravitational potential energy. So as I do work on a system, conservative forces, gravitational potential energy changes. A simple example of that, if I let this go, this has high gravitational potential energy right here. I let this go, this has lower gravitational potential energy. The displacement was down, the force of gravity is down, so the work is positive. A positive work changes the gravitational potential energy in a negative way. It decreases it, right? If conservative work increases kinetic energy, it has to decrease potential energy, right? That energy has to come from somewhere. That's the point of work. It transfers energy from one place to another. Well, substituting in here conservative forces with the conservative forces here, changing this to negative potential energy, and then adding gravitational or adding potential energy to both sides, we come up with the following equation. That the work done by non-conservative forces is equal to the total change in kinetic energy plus the total change in potential energy. Breaking up kinetic energy and potential energy, these are deltas, right? This is final minus initial kinetic energy plus final minus initial potential energy. Bringing the initials, which are negative on the right-hand side, over to the left-hand side, we end up with the initial kinetic energy plus the initial potential energy plus the work done by non-conservative forces is equal to the kinetic energy plus the potential energy in their final state. What this means for a system like a roller coaster, right? As the roller coaster goes down, friction between the car and the track saps some of the energy. That energy goes into heating the track, thermal energy losses. Those are non-conservative forces. It's friction. Or the wind resistance as the fast car moves through the air and you feel the air in your hair or on your face. That's drag force. That's a non-conservative force. So these non-conservative forces are typically negative, right? If you think about it, non-conservative forces sap speed. So imagine you have just a bowl, place just a dinner bowl and place a marble in that bowl and let on the side and let it roll, right? That marble, as long as you don't throw it down, if you just drop it, rest it against the side of the bowl and drop it, the gravitational potential energy will never be large enough for that to escape the bowl. It'll just keep on rolling around the bowl. But even in that case, where the frictional forces are very small, this marble will eventually, after many, many, many times rolling about, will eventually come to rest at the bottom of the bowl, right? The kinetic, it started off with some gravitational potential energy, which changed the kinetic energy, which changed back into gravitational potential, back and forth, back and forth, back and forth. But every time that object moved, friction was acting on it, sapping a little bit of its energy with every little motion. Eventually the friction takes away all the energy and the object is stationary at the bottom of the bowl. So the work done by non-conservative forces is negative. like friction, right? If an object is moving in this direction, friction is going in the opposite direction. F times d times cosine of theta, that's work, right? Work is force times distance times the cosine of the angle between those two things. If the displacement is in that direction, but the force of friction in this direction, the work done is negative. Since this value is negative, that means the final total energy will be less than the initial total energy. So take these total initial energies, add them up, subtract some work done by the non-conservative force, and you end up with your final energy. So the total energy will decrease with time. This brings us then to your book's discussion of the law of conservation of energy, which we'll talk about in a moment.